So good morning, everyone, and welcome to the Friday seminar. Today, it's a pleasure to have Qianshu Lu, who will tell us about the quality domain wall tension for post-inflation QCD.
Thank you. Thank you for coming to my talk today. I am a particle phenomenologist. I work often in the intersection of particle physics and cosmology. And today I'll be telling a story about there are some subtleties in the connection between the quality problem and the domain wall problem that we think people have overlooked slightly in the literature, specifically in the context of post-inflation QCD Axion. So now I'm guessing that most people in the audience know the strong CP problem and roughly the Axion solution to the strong CP problem, but perhaps you're less familiar with this pre-inflation, post-inflation divide, the two paradigm, and why specifically the post-inflation paradigm has been considered, interesting to look at in the context of axion dark matter. So I'm going to do some review of, basically defining every word in the title. I'm probably going to spend some time doing that, and then I will dive into the actual content of my story, which is this tension between trying to solve the quality problem and the domain wall problem. And I will be mostly talking about a very simple ZP solution to the quality problem and its relation with the domain wall problem. And the reason is that, of course, there are many models being constructed in the literature. But essentially, a lot of the feature can be understood just by looking at the simple construction. So that's why I'm going to spend most of the time on this. And if I have more time beyond this, which I don't really expect to, I might talk about actual model constructions that has a more complicated symmetry structure. Just to start briefly, let me introduce the strong CP problem and the axial solution. It's pretty hard. Strong CP problem. The strong CP problem is just a statement about the two essentially CP validating parameters in the quark sector. The first is the complex phase of the CKM in the CKM matrix that tells you how the weak interaction mixes the quark flavor. So there's a CP validating effect in that. And the second is the theta parameter, which is a parameter in front of the term GG dual in the Lagrangian. So there are two important properties of the theta parameter. The first is that because of the chiral anomaly, you can actually remove the theta phase and put it into a phase of the quark mass matrix. So really, to talk about physical effects, physical effect is going to depend on theta bar, which is this combination of the theta parameter and the argument of the determinant of the quark matrices. So that's one. Now another property of the theta parameter, which I'm going to use over and over again in my talk, is the fact that this parameter is 2π periodic. Of course, if you naively shift theta by 2π, the Lagrangian and action is not invariant, but I have normalized my term such that it turns out this combination of the field strengths is quantized. To be integers. So if you shift theta by 2π, your e to the I action shifts by e to the I 2π, and therefore the theory remains invariant. Okay, and the strong CP problem is the statement that experimentally we have observed the CKM phase the order 1, while the theta bar parameter is constrained to be less than 10 to the minus 9. This is this big hierarchy in the parameter that we call the strong CP problem. And the axion solution in terms of its minimal ingredient is just to postulate that there exists a 2-pi periodic field that couples the GG dual the same way that theta does. So now I'm going to postulate existence of some 2-pi periodic field, which I call theta A for axion, that couples the same way to the GG dual field tensor. Now, in terms of, depending on your model building, your axion coupling to GG dual might have some integer in front. Of course, it has to be an integer for theta A to remain 2-pi periodic. And for now, of course, this parameter depends on your specific model building, but now I'm just going to leave it as an integer that can exist in the theory. Bracket. Why is this a solution? It is because that the GG dual term after the QCD phase transition due to strong dynamics is going to generate a potential for our axion, which I can roughly write as 1 minus cosine theta A. Yeah, in other words, the strong dynamics generate the potential exactly allows the axion to dynamically relax theta bar to 0, or the minimum of this potential is at the CP even point. Okay. Even. Okay, so effectively, we are going to see an effective theta bar that has been relaxed to 0, and that is the axion solution. All right. Now the parameter n, of course, has a significance that it tells you the number of hills in this potential as the axion goes from 0 to 2 pi. And it just tells you when axion winds from 0 to 2 pi, how many hills you're gonna see in the potential right here. And now, in terms of where this field actually comes from, at least in 4-dimensional axion models, the theta A is simply the Goldstone boson, number Goldstone boson of spontaneously broken U1 symmetry, U1 Pechi-Quinn symmetry, in the name of Pechi and Quinn, who first proposed this solution, where U1 Pechi-Quinn has a mixed anomaly. And of course, this is not enough. We need the axion to couple to GG dual to be a solution to the strong CP problem. And to achieve that, the Pechi-Quinn symmetry needs to have mixed anomaly with a C3 color. And again, there are many different ways to construct axion models, but just so we have something minimal in mind, the simplest way, or the simplest way you might hope to achieve that is just to have some complex scalar, capital Phi, that's charged under U1 Pechi-Quinn and has some coupling with some heavy quarks. So this is complex scalar charged under U1 Pechi-Quinn, and those are some heavy beyond standard model quarks. And scalar has a potential such that U1 symmetry is spontaneously broken. So the complex scalar obtains a wave, and we identify the phase of the complex scalar as the axion. All right. So yeah, in general, some generic potential for phi is going to have this familiar wine bottle shape to achieve the spontaneous symmetry breaking. Okay, so this is sort of like the minimal construction for the axion solution to the strong CP problem. Now, the quality problem simply says if you look at the axion, of course, its 2-pi periodicity is an exact symmetry. You might even say it's a gauge symmetry because it identifies equivalent field configurations. But there is a continuous shift symmetry of the axion that's being broken by GG dual already. So now, if this continuous shift symmetry is already explicitly broken in our theory, so there is no reason to expect it to be protected from higher dimensional operators. So it's still okay. Continuous symmetry of sigma A. Yeah, I'm just writing down what I just said. These are the broken by GG dual. And of course, in the minimal construction, I have told you nothing that protected from further breaking. So there could be breaking in the form of operators, again, using my minimal construction, could be operators in the form of phi n to the 4 over n Planck to the n, where I just take my cutoff of my theory to be n Planck. And this is going to cause a correction to my axion potential. And in general, there's no reason for this, the combination of potential coming from this term and the original GG dual term to have aligned minimum. Right? In other words, this term can contribute a big correction to the axion potential that correct my minimum to a CP violating point, and this completely ruins my original solution to the strong CP problem. So we need this. We need this operator to be small or have a small contribution to the axion potential. And what that usually means is that if you, for example, now of course it depends on the value of the VEV that the scalar gets and in terms of how much you need to suppress this operator. Or for example, if the VEV that the complex scalar gets is on the order of 10 to the 12 GeV, and it's something like n needs to be greater than something like 15. So it's a rather large number. You need to have some reason to suppress the operators up to such a high dimension. Yeah, yes.
That's not the same n you had before.
Oh, I'm sorry.
It's probably a little one that I can't.
Yes, that's a little one. Yeah, or let me just call it K. Yeah, it has, so far it has nothing to do with each other. So far. So, okay, so that concludes my first point, the strong CP problem, minimal ingredient you need for the axial solution, and why you have a quality problem for this minimal construction. Any question about that before I move on?
I guess even the even the phi squared term, right? An issue.
Oh, yes, yeah. Actually, yes. Yeah, I didn't have to go.
Fine.
Yeah. Yes. Yeah, there is no reason for this to not exist, even though people don't write this down usually. But yes, I agree. Oh, then, but I mean, if you have something that forbid operator up to K2, then you automatically. So whether I write that down, usually it's taken care of. Yeah.
It can also be these operators have tiny coefficients, right? I mean, that's one of the causes of solutions is
yes. So yeah, if you imagine
these things all have exponentially small coefficients.
I think it's only from instantaneous effects and something like that.
No, even just like either separation in extra dimensions or lots of sites.
Right.
There's a sort of generic mechanism for ensuring the global symmetries aren't broken.
Yes. For example, 5D axion automatically by high quality. But I'm going to argue it's not post-inflation. So in my context, it's not. Yeah. Was there so much question? Okay. So now let me explain the pre and post-inflation operational paradigm of the axion. So by pre versus post inflation QCD axion, It's simply a question of whether this spontaneous breaking of the U1 Cauchy symmetry happened before or after inflation. That's the name. And it turns out that depending on the order of the symmetry breaking and the inflation, axions can have very different kind of cosmology. Now I will explain why that's the case. Pre-inflation, this means the Cauchy symmetry is already spontaneously broken during inflation. So then we have this wine bottle potential. Okay. And this is the shape of the potential during inflation. And well, since it's already broken, well, our axion is just going to sit at some point on that circle. Of course, during inflation, if you look at different patches, different Hubble patches during inflation, different Hubble patches are going to sit at different points along the circle, since they are unrelated to each other. But in terms of what we can see, we're only going to see one of those patches. Okay. So effectively, what that means is that post-inflation, you look at the value of theta A from 0 to 2 pi, our universe is going to have a value of the axion field that's somewhere between 0 and 2 pi. Okay, we don't know what, and there's no way to predict this because again, this is just by random chance where our Hubble patch happen to sit along the circle. So it's just some random value that the axion takes in the universe we can see. Okay, so I'm going to call this value theta A. So this is essentially there's some quantum fluctuation on top of it. Essentially, the distribution of axion field value in our universe is some narrow strip in the range between 0 and 2 pi. Okay, now what's going to happen? This is right at the end of inflation. This is the distribution of axion field value. Now what's going to happen later, much later, when the QCD phase transition happens, I told you that the strong dynamics generates a potential for the axion. So it's going to do potential on top of this. And let me just draw the example of n equals to 2 again. It's roughly like this. Okay, so at temperature less than roughly lambda QCD, strong dynamics generate a potential for the axion. So now experiencing the potential, the axion is going to now coherently oscillate around this minimum in the potential. And this coherent oscillation means that axion now effectively behave like matter. This is just the fact that it's oscillating around the approximately quadratic potential minimum, and we can show that generically a field oscillating around quadratic minimum behaves like matter. And of course, this naturally contributes some abundance to dark matter. But yeah, important point is that there's not really a way for us to predict what the dark matter abundance is going to be, because clearly the energy density of my fluid and my abundance of axion dark matter is going to depend on the initial oscillation amplitude. And as I said, well, it's just an initial condition, right? And we don't have a way to predict what the initial condition of our universe was. Okay? So this is what happens if you have pre-inflation. Pre-inflation QCD Axion. Now with post-inflation QCD Axion, the story is a bit more complicated. Also a bit more interesting. So just like the name says, post-inflation just means that the Cauchy symmetry breaking happens after inflation. Or really the important point is that at some point after the universe has reheated, the Cauchy symmetry is restored. Post-inflation is after inflation stored, then broken.
Does the period of this oscillation also like matter or not?
Period?
If you have more peaks in principle, like if you have steeper potential. Like this.
Yeah, I suspect it matters in the, no, it's always going to be a quadratic minimum.
Oh, I see.
Yeah, so it's always going to be matter like.
Locally, yeah.
Yeah. So not so much of the bigger picture. Okay, so post-inflation, usually people say just the Pechi-Queen symmetry is broken after inflation. But the important point is that it was restored at some point after inflation, after the universe reheated, and then it was broken at temperature lower than B. So now what happens? So at the end of inflation, let me draw the same picture. We have theta A from 0 to 2 pi. But the high temperature, so I said by definition, the Pechi-Queen symmetry was restored due to thermal correction. What that means is that my axial potential is not my wine bottle. It's just quadratic because of thermal correction. So I have theta A behaving like this, where my wine bottle, 0 temperature wine bottle potential is here, but I have a quadratic potential due to thermal correction. It doesn't, well, at this point, it doesn't really make sense to say what my theta A value is. Okay, I have not even spontaneously broken the symmetry yet. But now, when the temperature drops, less than B, or as the thermal correction gets weaker, I'm going to approach my 0 temperature wine bottle potential. But before, because of the quadratic correction, my axion was sitting at the top of the hill. Now, of course, the quadratic contribution is gone. It doesn't like to sit there anymore. A small fluctuation is going to cause it roll down the hill. Now, what that means for the theta A distribution is that, yeah, it's going to pick whatever I want. And it's going to, in particular, it's going to pick all the value between 0 and 2 pi. There's no reason for it to be preferentially occupy any region over the other. So this distribution of my axion field is going to look like this, which is very different from the pre-inflation case where it was some narrow range between 0 and 2 pi. Now, one thing that happens at this phase transition is the production of cosmic string. It's just an infinitely long string-like object where, as I go around the object in space, I'm also winding around. The circle in the vacuum manifold. So I can do this. I'm seeing the winding of the axion potential, and the topological defect of this cosmic string, it just forms by the fact that different uncorrelated region in the universe is going to randomly pick axion values between 0 and 2 pi, and by chance you might just get a configuration like this. So now something a bit more non-trivial as production of cosmic string in the post-inflationary axion case. Something more happens when the temperature drops below the QCD phase transition. Now, as the temperature drops below the QCD phase transition, then I said, repeated many times at this point, that QCD dynamics is going to generate a potential for the axion. So again, let me draw an example where n equals to 2. Okay, so a potential, cosine potential with 2 hills. I had an axion distribution, unlike before. Now I have an axion distribution that goes all the way from 0 to 2 pi. So different region of space is going to fall into different minima of this potential. What that means in terms of the topological defect is that, so remember before we had a string where as you go around the string, you were going from 0 to 2 pi in the axion field. But of course now, because of the potential, as you go from 0 to 2 pi, you're going to hit those hills, which means now the axion string is going to be attached, in this case, 2. One string is going to be attached to 2 gigantic sheets of energy density, which we call domain walls. This was my string. And each string I now have infinitely big domain walls attached to them. And clearly the number of domain walls attached to each string is closely connected with the n in my cosine potential. All right. So far, okay, the story is a bit different between pre-inflationary and post-inflationary QCD axion. But now the important point comes. When the number of domain wall attached to each string, which I'm going to call NDW, sorry, number of domain walls string. Very different dynamics happens when, depending on whether NDW is 1 or greater than 1. When NDW is greater than 1, and easy to see that my whole string wall network is going to be stable because I have a network of infinitely long strings. And after the QCD phase transition, now I have infinitely big sheets of domain walls attached to the strings. And as the walls and strings move around, it's just an infinite network that has no boundary. So and there's no way for it to decay. As infinite extension. Size and is stable. And it turns out that stable domain wall is a disaster in cosmology. The main reason is that it's really a gigantic sheet of energy density. It's a big sheet of energy density. Okay? So it's going to redshift slower than anything we're familiar with. It's going to redshift slower than radiation. It's going to redshift slower than particles. So what that means is that its energy density, even it might start small compared to the total energy density of the universe, is going to very quickly dominate over everything. And our universe, the cosmology we see today is not consistent with the cosmology being dominated by domain walls. So essentially, this is a cosmological disaster.
Usual mechanisms here, domain walls, which just have a tiny breaking of the symmetry, so there's a pressure.
Yes.
That will not work here because that same tiny thing will ruin the flatness of the axion.
Exactly, yeah. And specifically for QCD axion, people have worked out the parameter space, and it just doesn't work. Yeah.
If n equals 1, is
yeah.
right?
Yeah. So yes. NW equals 1. Then of course the same. Now my network has a boundary because every wall is bounded by 2 strings. String. And the same clearly can collapse. So the string wall can collapse. And in this case, we have the added benefit of that in principle, your axion dark matter abundance is now exactly calculable. Okay? Because compared to the pre-inflation case where we had no idea where this initial condition is, for post-inflation, the initial condition is essentially everything between 0 and 2 pi. Or it's the same story that thermalization helps us get rid of the initial condition. So when NDW equals to 1, string wall network can collapse. And this is going to contribute to the dark matter abundances, the collapse of the network producing axions, contributing to dark matter abundances. And this is, in principle, exactly calculable. I think it does not have the same initial condition uncertainty as the pre-inflation case. I say in principle calculable because it's easy to see that the scale where the cosmic string is being produced, which is the Paget-Quinn breaking scale, and the scale where the domain walls are produced, which is lambda QCD, they are hugely separated. And in order to understand how the existence of string contribute to axion dark matter abundance, you need to, if you're trying to simulate the whole system, for example, you need to have a simulation resolution that can resolve the core of the string while the whole box being big enough to be the Hubble volume at the time of QCD phase transition. Okay, so that's like a e to the 70 separation of scale. So that's why I in principle here because of the huge separation of scale. Still making this a very
the problem of numerically simulating what these things look like, what the networks look like.
Yes, and there isn't really. Well, analytically, we certainly don't have enough understanding to be able to say what is even the spectrum of axions being produced from.
No uncertainty in the cosmology that got you there because the strings dominate over everything on the way to this last point. No.
Yes. Sorry. Are you saying that? Can you repeat?
Sorry. I mean, before the walls form between the strings, don't we get after the PQ transition an order one fraction of the energy density of the universe in the strings?
Energy density in the string.
What's dominating the universe after the Paget-Quinn transition?
It's the background cosmology is standard. Okay, so it's not. Yeah, the string wall network is never dominating.
Why don't we get a lot of energy density in the strings to begin with?
Why wouldn't you get a lot of energy density?
And they redshift more slowly than everything else too. So.
Oh, but they reconnect. So the same.
Oh, right. Because that's
and they stay like
they carry each other up. Yeah. I see.
So yeah, they never. Well, at least that's what we see from simulation.
Yeah. Right.
Yeah.
That's a big deal.
Sorry, I have another question. So, when you get like other densities of fluctuation, so there will be fluctuations in the density, right? Depending on where you, different regions of the universe you have the axion in place. Are they, do people,
trying to
understand this? Or
yeah, so that's related to the fact that your simulation boxes have to be big, that you're not like focused on a small region that you might move back. Is that?
Well, I'm just wondering that there might be a constraint. So now the fluctuations in the dark matter seem to be unrelated to, or not obviously related to the density, like primordial density fluctuation.
Oh.
On top of the isocurvature constraints.
Yeah. So pre-inflationary, well, there's a clearly isocurvature constraint there.
Exactly.
In post-inflation, post-inflationary case, I'm trying to think why that is not considered a problem.
Post-inflation is just like every other way of making dark matter, right? So we're still just changing the clock. We're just fluctuating the clock during inflation. So yeah, I think it's just adiabatic.
Right. I understand the thermalization make it adiabatic. I'm a bit confused about the topological defects.
Well, I guess maybe the question is how big is maybe the horizon scale when the Paget-Quinn symmetry happens.
Yeah, it's definitely very, very, very. Yeah, I'm trying to think.
Distance corresponds to now, I guess maybe if it is a relatively short distance, then
yeah, I was trying to think about the CMB, the constraint where we have.
It's obviously a much higher temperature than the CMB.
Right.
Yes.
right.
But yeah, so it's right. Yeah.
Yeah. Yeah. Sorry, I'm not giving a very straight answer. Yeah.
Practice, it's adiabatic.
Yes. Okay. So right. So clearly, NDW equals to 1 is what we want. It doesn't contradict cosmology. cosmology we see, and also in principle exactly calculable, although there is a huge difficulty associated with that. The difficulty has not.
Sorry, Qianshu, just a tiny thing. I don't understand why the size of the core matters at all. I mean, presumably everyone is just simulating them with like.
The thing is, you cannot treat it. You have to look at essentially how this. If you want to really predict how much axion is being produced, you need to understand how this topological defect unwraps, like in terms of the complex fields and everything. You can't, because if you are not resolving the string, you're essentially just looking at some point defect and you have no idea about its dynamics, which is fine until you're claiming that every energy density and every complex field is
something simulated by some effective theory with a coupling between the string, the infinitely thin string, and whatever's involved. I don't. I don't know how people do it, but that
yeah,
but this particular theory, I mean, for extracting the couplings with spectral theory, you have to take this microscopic model to work it out. That part you could do just analytically. As far as the simulation goes, I would think you just put whatever couplings you have. Then we'll go for the string, and then you just coupling.
But even
the bulk modes and that.
But even when the strings are annihilated, because after it collapses, you just have
Are they cutting themselves and annihilating all the way down to the scale of the?
This whole thing annihilated because it's going to have opposite winding and
right. But isn't most of the particle, most of the production, whatever? Are you saying that all the excitement happens when they cross each other?
Actually the dark matter abundance depends strongly on the string tension.
Okay,
so
maybe I can ask.
Yeah. At least so far, so people try to do simulations across, of course, not E to the 70, but across a shorter range of scale. And what they found is that the dark matter abundance, well, heavily depend on the properties and of the topological.
I guess what I was asking is most of the axions that are produced being sort of radiated when the strings are moving around, or are they being produced when they cross and reconnect? If it's coming when they cross and reconnect, then I can imagine that you need to know what's going on at the short scale. If it's mostly coming from, radiation as it's moving around, that should be calculable without those details. So
but this is not even reconnection. This is the strings are
fine. Not reconnection, right? The whole, but
yes, they are. Right? Yes.
So
is that
when is most of it being produced? Is most of it being produced when they finally smash into each other?
Yes.
Okay.
Yeah. So it's not the initial.
It's not the wobbling around and radiation.
Yeah. Okay. Yeah. Right. Right. Okay.
Yeah. And it's probably also this topic from your seminar, but what would the axions be like today in such a scenario?
Yes. So the spectrum of the axion being produced is, well, the simulations, of course, with limited dynamical range are showing that they have momentum roughly on the order of Hubble at the time of collapse, which makes it cold. So they're not warm if you're worried about that, because axions are very light and it looks like you might be injecting a lot of energy to make them hot, but it turns out that the momentum are very small.
But they're not coherent oscillator or anything. It's just like particles. It's like a bunch of particles of axions.
Yeah. Okay. Does that answer?
It's not coherent on any reasonable scale?
Yeah, I mean, that was...
No.
No, I see.
It's almost like, it should be more like a non-thermal particle production. Yeah, not the coherent oscillation, like the pre-inflation case. Okay. So there is some difficulty associated with understanding the system, but of course, like I said, people have tried to do it as much as they can, and post-inflation. And what people have done is just to look at the minimal model I have mentioned, a complex scalar, charge 1 under U1 H plane, and assume NDW equals to 1. So 1. U1 H plane, NDW 1. Simulate. Okay, and then the most most advanced simulation in this regard came from quite recently, 2021, some complicated numerical method to get as much dynamical range as possible. And what they predict is that if axion is all of the dark matter, they predict that MA, the mass of axion, is in this remarkably small range. All right. Of course, I have mentioned that there is great difficulty associated with understanding post-inflationary dynamics. So I will take this number with a spoon of salt, not even a grain. But today I'm not going to be talking about whether the simulation is correct or not.
And what's the F axion? Sorry, I can't convert.
Sorry.
What's the F axion?
Yeah, FA. Sorry, I have to do it. 6 MeV is 10 to the 12.
Okay.
So yeah, yeah. So sorry, 6 micro EV is 10 to the 12.
So we're talking
10 to 10.
10 to 11.
10 to 11.
Yeah, 10 to 11, 10 to 10.
Which is,
I had the super.
but it's also surprisingly similar to the estimate you got if you assume it was coherent.
If you
It's surprisingly similar to the estimate of F axion you get if you assume the production was coherent.
Yes, yeah. Yeah, I'm not sure if something's going on there, but okay. So, right, today I'm not going to debate the accuracy of this number. I would say take it with a spoon of salt. But what I'm going to argue is that this minimal construction, assuming NDW equals to 1, is not the correct model to look at if you take the quality problem seriously. And it's not even, of course you might say, well, people wanted to simulate. Of course they take the minimal simplistic model they can take. No one said that this is the correct axion model. I'm going to argue that this is not even a good approximation, what you might imagine to be the correct axion model in this specific context. And that's precisely because of the quality problems.
Sorry, Qianshu,
Yeah.
this NDW is the same as the N? Is the same as
no. Right. In this case, it's the same as N.
It's the same.
Yeah, because N determines the number of hills. N, yeah.
You also remind me quickly, Qianshu, that the Rafelt bound used to be 10 to the 10, right? For axions from supernovae, and then there was some controversy years ago. I can't remember which.
There's some. The bound is gone because of some misunderstanding of some. Was it like plasma shells around supernova? But that bound is essentially just null for axions. They were saying that there's no way for some mechanism that axions cannot escape and contribute to cooling. So yeah, otherwise this will be ruled out. But
is the claim that the Rafelt bound is gone?
The supernova.
Yeah.
19. Yeah. Yeah, because that was based on some energy loss, and there was some misunderstanding apparently of the structure of plasma matter around the supernova. So yeah, it certainly does not exist as a solid axion bound anymore.
Okay. I thought it was a matter of factor of a few in what the bound was. You're saying that the bound is actually gone. All right, I have to see it. All right, thank you.
All right. Okay, so sorry, let me write down why I'm trying to argue. I claim if you take the quality problem seriously, with the quality problem in mind, not a good approximation to any models. For the post-inflation. So I'm not arguing about the accuracy of the simulation. I'm claiming that the starting point, the model they try to use, it's just not a good approximation to anything. We think it's not a good approximation to any models if you try to solve the quality problem.
But there is a solution. I mean, it's not using symmetries officially, but I mean, we can do the thing that I said earlier. You can, have some extra dimension, say, or you can say 4 dimension if you want. But you have Pache point gauged in the bulk.
Yeah.
You break it on a brain on the other side, and you have your scalar on our side, and that gives an exponential suppression to the operators that you're worried about. And so that could be a theory with NDW equals 1 and everything.
Right. There certainly exists NDW equals 1 theories, but for example, the 5-dimensional case, you never restore the Pache symmetry in your cosmology.
No, I'm not saying the axion's in the bulk. I'm just saying that it's a 4-dimensional. It's exactly your theory, exactly your 4-dimensional theory.
Right.
I'm just saying that to explain why you don't have this higher dimension operator, you imagine that somewhere above the PQ scale, there's a 5th dimension or some extra dimension. PQ's in the bulk. You add some fermions, cancel anomalies, blah blah blah. You just break PQ far away, and so any breaking of the PQ symmetry will be exponentially suppressed by the distance. I mean, this is a very standard mechanism for using extra dimensions to get tiny, exponentially small numbers. Flavor, photon decay, this, that. But axions was one of n things that you could do in this way. So in other words, it's easy, and we consider this purely 4-dimensionally as well. It's nothing to do with extra dimensions.
I see. Sorry, you're not saying that the axion. You're not saying the axion. This is not the same as those A5.
No, it's not the same. A5, I would agree.
This is like sequestering.
This is like sequestering. Exactly. It's like exactly.
Yeah, I'm not thinking about the sequestering.
So it's not. I mean, it's not in the class of things you're talking about where there's a symmetry that's prohibiting.
Yeah.
There, of course. Well, you'll tell us the rest of the story. But I'm just saying that there are simple non-symmetry ways which are part of the, canon of how people imagine generating tiny numbers in very simple ways. Which are not guaranteed by symmetries. In that setting, you certainly restore PQ. I mean, it's a way of generating your 4-dimensional.
The exponentially small.
Yeah, it's just your 4-dimensional model with exponentially small coefficients.
Right.
No, it's a really simple idea. It's a very simple, ubiquitous idea. It doesn't have to be RS. It doesn't have to be extra dimensional. But it's just the general point that you don't need symmetries to explain why some operators have exponentially tiny coefficients. There can be other mechanisms. Not officially symmetries.
I see. Yeah, I agree. Okay, so if I talk about the ZP, okay, so I should say symmetry solution.
Yeah, certainly people mostly talk about symmetry solutions for a long time.
Yeah, and yes. Okay, so let me see. Okay, so the simplest symmetry solution you might imagine for the quality problem is just impose that phi is charged under some ZP symmetry that's a subgroup of U1 Pache plane, and you want to gauge it to be a protected symmetry, and of course, immediately, if it's charge 1 under ZP, any operator up to is forbidden up to k equals to p. Okay. Equals to p. But to be able to gauge this subgroup of U1 Pache plane, of course, well, we said that Pache plane has a mixed anomaly with SU3 color. So you need this subgroup to be anomaly free. PP needs to be anomaly free, which in terms of the coupling of the axion, it just turns out that what that means is that the coefficient of the axion coupling to GG dual has to be a multiple of P. S can be integers. S is integer. And well, it's easy to see this if you don't have to think about anomalies, but just think about how the ZP symmetry is acting on theta A. It's going to shift theta A by 2 pi over P. Of course, we said it's the thing in front of GG dual, the whole thing needs to be 2 pi, is only 2 pi invariant. So if you want the theory to be invariant under this shifting of 2 pi over p, you need the coefficient to be remarkable. At this point, okay, you might say that, okay, now I have a problem because my NDW, which is n, is SP, and that's clearly greater than 1. Of course, that's way too quick because that's a bit too fast. Well, it is true that if you're counting your domain wall number against theta A, you will see after the QCD phase transition generate the potential, as you go from theta A from 0 to 2 pi, you will see SP number of domain walls. But that is too fast because clearly, with NDW equals to SP, I know that my neighboring minima in the cosine potential is SP theta A are separated by theta A going to theta A plus 2 pi over SP. So clearly, if I can model build such that S equals to 1, the neighboring minima are exactly related by the ZP gauge symmetry. So 1 equals to 1, minima related by ZP, which is a gauge symmetry. So what that means is that in addition to the 2 pi periodic variable theta A, in my theory, I can identify another variable or another field that's also 2 pi periodic. Check out theta tilde, which is E theta A. Okay, so the 2 pi periodicity of theta tilde is ensured by the ZP gauge symmetry of my theory. And now I can rewrite my P theta A 32 pi square GG tilde to be theta tilde 32 pi square GG tilde. Okay. And if you now identify this to be your axion, you have domain wall number equals to 1. And when people model build in the literature, this is sort of the extent they go when they claim they have solved the domain wall problem, which is to say they construct, not with ZP, but construct some more complicated symmetry structure. And they say because of the bigger gauge symmetry, I can identify neighboring minima in my axion potential to be gauge equivalent. And that solves the domain wall problem. But that is, again, a little bit too fast because we know, in some sense, the fact that the neighboring minima in my axion potential being gauge equivalent is a necessary condition, but it's not sufficient. So the fact that, so this is necessary, but not sufficient. Because remember that to really solve the domain wall problem, what we need is existence of cosmic strings where one domain wall can end on it. Okay, so solve problem. In some sense, we need NDW equals to 1 strings, not just NDW equals to 1 state in our theory. So, and now let's think about the minimal, again, come back to our minimal example of phi being charged under the one Pechi plane. In this example, it's easy to see that the string that we want, where theta tilde 1 is by 2 pi, is not going to form at the time of Pechi plane phase transition. Why is that? So if I draw my wine bottle potential for my phi, so imagine now I have some C3 subgroup of U1 of U1 Queen, it means that I have three points along the circle that are gauge equivalent, or the three segments of the circle are now gauge equivalent. At the time of Pechi-Quinn phase transition, there is no dynamical reason. I have mentioned how the cosmic string formed by the axion initially sitting on the top of the hill, falling down the circle. And there's no dynamical reason for the axion to suddenly only fall down this sub-segment of 2 pi. Okay. So at phase transition, we don't form the string where say the tilde 1 by 2 pi, which is what we needed, but instead we only form the original the string where the original axion 1 by 2 pi, and those are precisely the problematic ones where NDW equals to 3 in my case, or equals to P in general. Okay. So this is what I meant, that just simply stating that the neighboring vacua are gauge equivalent is not enough. You need to dynamically ensure that the correct string forms in the early universe. In this specific case, yeah, since I only have 2 minutes left, let me just elaborate a little bit more on this simple case, and I will conclude. Now, in this specific case, of course, you might say, well, there is an easy way to generate the string I want. Now I'm talking about the symmetry structure of the theory in the IR, where I have a Z3 subgroup being engaged inside of U1 Pechi-Quinn, but we know how to dynamically obtain such a gauge theory, which is the Higgs some gauge U1 prime, the gauge U1 prime down to Z3 by some Higgs, that has charge 3 under 1. So, and from this, so this is on top. So this happens sometimes before. You can imagine some phase transition happens. Like this happens before my Pechi-Quinn symmetry breaking by my complex scale. And I have argued that here, I only form strings where theta A points by 2 pi. And similarly here, I will form strings where the phase of theta, phase of my Higgs, which I will call theta H, points by 2 pi. But because the Higgs is charge 3, this is precisely the theta tilde string we want. Okay. So this is one way of dynamically. So what that means is that in the universe, after my Pechi-Quinn phase transition, I will have 2 kinds of strings. One formed by this earlier Higgsing of a gauge U1. I'll have 2 kinds of strings. These are ones where the set Higgs 2 pi, and I'll have axion strings. And this one will have, yeah, let me just continue with the Z3. This will have NPW equals to 3. But this string will have domain 1 number equals to 1 after the QCD phase transition. Okay, so this seems like it's again completely sensible solution to the domain 1 problem. But an important fact here is that this earlier phase transition that spontaneously break the gauge U1 prime, the scale of that has nothing to do with the Pechi-Quinn scale. Okay. In particular, the string, here string tension is going to scale as the VEV that the Higgs got squared, while the tension of my axion string is going to scale as my axion VEV squared. Okay, but we know from from simulations that people conducted that the final axion abundance generated from the collapse of this whole thing, we expect it to strongly depend on the property or the tension of the cosmic strings. So what that means is that before we had this hope that we can, just work a model with NDW equals to 1, and that gives me a very precise prediction of the axion mass. But now what happens is that now I have another dimension of the parameters, and clearly depending on the scale of my higher symmetry breaking, the correct mass, well, which way does it go? This way, I think. Sorry, I didn't draw this plot earlier, but clearly there is some now a line in this two-dimensional parameter space, and in terms of the axiom, and this has nothing to do with my FA. This is an entirely separate independent scale, and if you look at, if you are simply trying to predict what the axial mass is going to be, you just lose the control that you're hoping to have for this post-inflation axion case. Okay.
I don't understand the picture anyway. You've got these strings with charge 3.
Yes.
Which at low energies become boundaries with domain walls.
Yes.
The other ones are also boundaries with domain walls.
Yes.
But the other ones perhaps can shrink. But the only because you gauge the Z3, yes. The only thing I can see is that the bad ones, the charge 3 strings, which are boundaries with domain walls, those domain walls could end on this very heavy strings. But in practice, that probably won't happen. It's too hard to nucleate them.
I'm not nucleating them. I'm forming.
Those you already have. Some of those you have, but they're unrelated to the domain walls you generated. I don't see the mechanism by which the domain walls will disappear.
Oh, sorry. Yeah. Yeah. In this case, I skipped a bit of a step in the sense that I need to charge. Yeah. Sorry. Perhaps that's the confusion. I need to charge my Cauchy-Plane scalar under the U1 prime as well. And my axion is going to be a linear combination of the phases from the two. So that's why winding of theta H and theta A can both be considered a winding of my true axion, which is neither. And then this is truly my real axion winding number 1, and this is truly my real axion winding number 3. And then so I will have network, so the domain wall should not be colored. I will have network of string where there's an axion domain wall. Some of the string bounds 1 axion domain wall, some of the string have 3.
That I understand.
Yeah, and you hope that you have high enough abundances of these strings such that you can get rid of domain walls even from these.
I find that hard to visualize.
Yeah. Well, if I have like say the 8 string, yeah, it's perhaps. Yeah, so I would say. Yeah, because people have focused so much on the minimal scenario, it's like no one knows. Well, maybe by percolation theory, I can work out how often this happens. But this is what you need. I agree. Yeah, and at this point, yeah, I don't really have an idea of how likely this is probabilistically.
Well, because domain walls are potentially so disastrous, I would definitely worry that would not work well enough.
Yeah, so I agree. Maybe you would say that this decays at the rate that's much lower than if you only had the correct string, and then it might be enough to ruin cosmology. But at least there's some room to think this work. But but clearly, if you try to solve the domain wall problem this way, you just ruin why you like the post-inflation QCD axion in the first place. And that's why, yeah, I've only presented the simplest story of ZP, but it's just a very quick example showing that, it's fine that people want to simulate and trying to predict, but if you try to solve the qualitative problem from a symmetry solution, you're really very quickly losing to the predictive power that you hope to have in the first place. Okay, I'm over time. Okay, thank you.
All right, any extra questions? guess we've had a lot of questions already, so maybe let's thanks Qianshu once again.